one of the most popular when it comes to metal additive manufacturing. But while we were actually discussing about technology, so if you observe the kind of a component so that you can actually manufacture or 3D print, it's like a more of a small component, and also the you need to also actually restrict the number of material, the composition, right? Which means, say example, if I want to actually play with multiple material, or if I want to actually go with larger scale in terms of the print, or the size of the print, you want to actually print bigger component. So it will take a lot of time, because as I said, the one of the constraint that we have, the size of the powder, right? The size of the layer thickness. So since the layer thickness, when it comes to the powder bed fusion, usually small, right? Because when you have the size of the powder is small, like example 80 to 100 micron, right? So you will not be able to achieve more than 0.5 layer thickness, right? So even that itself is difficult if you actually spend more when you actually try to play with parameters, so you will be able to achieve. But however, so if at all you want to actually speed up the process, right? So we had to actually go for multiple lasers, right? Where you can actually print multiple with the multiple lasers, you can actually speed up the whole process. And then there is always question, right? If you want to actually increase the number of lasers, right? Which means you also need to actually work out the strategies, right? You need to work out on how to, where to, which laser will actually deposit which area, and so on. And then they should not actually interfere between the lasers, right? So, and if you want to also go for a multi-material deposition, or sometime you want to actually go for a composite structures, or you want to go for a different in terms of structures in gradient or composite or so, etc. So it's quite challenging when it comes to the powder bed fusion. I think that's where the directed energy deposition will actually will solve some of the issues when it comes to the multi-materials, or when it comes to the scale of the size of the component, right? So if you talk about the technology, so the technology is actually something like where you have the think about you need to create a part, right? Create a part. So you basically think about like FDM technology, like that we have actually talked about it. So where we saw that the filament is actually will be coming out of the nozzle, and then as you actually move forward, and then you will be actually fusing the material, right? So and then immediately it will actually start solidifying it, right? The idea is same, but and then the kind of the fusing method slightly vary, right? So there we didn't had any lasers for a fusing of the filament. But here what we need to what we have to have this, basically we need to have lasers, right? Or we need to have different other mechanism or methods to fuse the powder or the wire. So it is basically you need to create a part, right? Or melt, right? The part maybe or the input may be in the form of a filament, or a wire form, or maybe in the form of powder. So what you do is actually create a part by melting, at the same time depositing, right? So and then the material which will be actually coming either from either in the form of a powder or feedstock. So if I talk about as I said, it is similar to the DED, or sorry, power FDM, but only the you have the change in terms of feed, or in terms of fusing of the material. So what happens here? So you have the laser, or which is nothing but energy beam, right? So energy beam is also actually focused. Say example, you see if this is the bed, right? So you have basically the bed, and then you have the laser is actually coming from the in the middle sometime, or you can also some configuration from side also, right? So when you actually see that, say in one case you will have the laser is actually coming from the middle, right? The powder will be coming through side, right? So but and then you have the focus point on the surface of the plate, which is basically where all together will meet at focus point, right? As soon as the laser actually come and meet the powder, which means it will immediately will melt, right? And then since you are not actually staying there, right? So your bed actually will move like this, right? And then you will have different path planning and then etc. So as you actually move away from the focused point, which means you will be able to get the deposition, right? So that is simple when it comes to the deposition, right? But and then think about how you can actually feed that material, right? How, what form of a material, like whether it in the form of a powder or wire form, right? So when we actually focus the beam, which is a narrow region, which is used to heat the material that is actually being deposited, right? And then, as I said, unlike the powder bed fusion, where the powder is actually spread, on the bed, and then you will be actually selectively fusing or selectively melting resin, right? But here we are actually not, powder is not actually spreading entire bed. Instead, you are only adding the powder, right? And immediately you are actually melting it off, which means when it comes to the efficiency of the powder or the usage of the powder, right? Usage of raw material here is almost 100%. Unlike when it comes to the powder bed fusion, so you may be spreading entire bed, but you may be only melting 30% or 40%, sometimes even less than that area, right? Or sometimes even more also. But and then there is also a lot of powder where you may not be actually melting it, or you may not be actually fusing it, right? But of course you can actually recycle it. But here we don't need actually that much powder or that much raw material or that much wire when you want to actually fuse it or when you want to actually make a component, which means whatever the powder or whatever the wire that you are actually fusing, it will 100% will convert into product. Of course, there are cases like where you may have some evaporation or melting and so on. So that is considered as a losses. But and then overall, you will find that amount of the material that is actually required or the losses usually will be less in this case, right? So they are basically you can see that advantage when it comes to the technology. See, if you see that the technologies in terms of the different, in terms of the principal point of view. So here we have actually talked about initially spreading the powder, and then you are actually selectively melting on some region only, which means this entire portion is not at all melted. Maybe there may be partially melted, the region which is little closer to the already deposited. So here you can see that the laser is actually coming, right? So where you have the powder is actually coming from the side, right? Here you can see this is a powder, the nozzles, right? This is a laser. So as soon as powder is actually will fall on the surface of the build plate, right? The laser actually will immediately will come and will melt this region. Since as soon as you actually melt it and then you actually move away from or you have the motions which you actually form this is actually the deposited layers, right? And then you are about to deposit this region, right? So this is what you actually considered the layer thickness, right? So then you have the different tracks, etc. Now you may have a different in terms of in this case, say the example the powder, right? But you can also actually go for say wire form. You can also actually feed the wire, and then you can actually use the laser for melting the wire, right? And then as soon as you actually melt, and then you simply move away from there, move the plate, which is basically X and Y, right? And then you actually get the position, right? Sometime you may have a powder form, or you have the wire form, or sometimes you might also actually observe the different configuration. The powder or the wire can actually come in the middle, right? So, and then side you will have multiple lasers will be actually coming, right? And then at the end of the day, you have to remember that how to actually melt, how to fuse your powder, how to fuse your wire, whichever you are actually feeding, is what matters. And then how uniformly you are actually melting that powder, so that you can actually melt powder or wire fully, right? So otherwise, you will not be able to actually melt, and then your properties may not be good when it comes to the deposition, right? So there are different variants when it comes to the technology, right? So example, as I said, so you can see that different the feedstock, right? So powder based feedstock, and then you have the wire based feedstock, right? This is basically what how you are actually feeding your materials, right? So as I said in the previous slide, that you need to see how you are actually feeding. You feeding through the side or in the middle, but again at the end of the day, how effectively you are actually melting. It is nothing but you might have actually seen a tungsten MIG welding or tungsten welding or MIG welding, etc. It is similar. Or sometimes you may also have based on the energy, right, type of energy, you can also actually use a different energy for melting the powder or wire, right? So example, there are heat energy, which is you might have actually seen laser based, and then electron beam based, and then plasma, and then electric arc. So these are very common that we have actually seen, which is actually you might have heard TIG welding or MIG welding, right? So they actually fall under this category, right? Where you actually heat is basically your plasma or electric arc, right? Which is also nothing but wire arc additive manufacturing processes, right? So, and then we have the laser based, where you will be actually using different lasers for melting your powder or wire. And then you have electron beam based technologies, where you will be actually using electron beam for melting powder or wire, right? And then you have another energy, basically kinetic energy, which is cold spray, where you can also actually use different cold spray technique for depositing the layers, right? So these are the commonly that you will actually find DED variants that and then when it comes to the scale of the component, that when it comes to that what is the size of the component, right? It is actually it will depend on the input or the size of the powder, and then size of the wire, right, or the diameter of the wire, right? So larger the diameter of the wire, and then you will be able to actually, of course you need to actually play the parameters, like example the speed, right? And then based on the speed of your process, you can also get different heights, and then you can increase the speed of the printing process, right? So you can have a based on the application, but with this technology, you will be able to print the large scale component. There are cases like they have printed more than 3 meter and then 4 meter long components, but and then there are again a lot of other constraints, that how well in terms of surface finishing, and then in terms of mechanical properties, etc., right? So there are again different variants that you will actually find with the technologies, right? So as I said, early when the technology started, it is like a more of a laser engineered net shaping, which is nothing but the lens. So it's basically the net, also people call it, it's by why they call it as a net shaping. It is basically you are almost getting the actual one but not actual one, right? Which means you need to actually still go for some more post processing of these technologies, right? So, and then there are few more technologies. Again, all these technologies actually works on a similar in terms of when it comes to the deposition, right? So that's why I name this variants like one wine and then many bottles, because you may have the same in terms of a concept, but and then you have different names. As I said in the previous class also, when a company starts something in a similar line or similar technology, they will not actually have the same name, but they will actually come up with a different name so that they can avoid any IP issues, etc. Right? So you have that early technology. Another early technology is actually directed light fabrication, and then this is a much early technology, direct metal deposition, where I think they, in fact, early they also developed a feedback system, right? So example, how I will know how much the height of the deposition is actual, that I have actually, because when it comes to the this technology, when powder is actually feeding it, sometimes powder actually also can fly, right? Or based on the flow rate of your gas, right? And then how you will actually ensure that your the powder is actually being deposited the actual height of the component. So that's where lot of feedback systems are actually in place, so that you can actually see how much material is actually being deposited. And then I think most commonly later on people have actually classified all this technology under one umbrella, which is a directed energy deposition, right? You have a 3D laser cladding, and then laser generation, and then laser based metal deposition. So there are so many other variants after that, right? So you can actually find many similar technologies when it comes to the concept. There may be a few more names which I may not be presenting here, but and then if you see that typical schematic of all the DEDs technologies are something like this, right? So where you will actually find the laser generator, where if not laser, you may have electron beam, right? Right, and then you have the typically the head, which is uh, where you actually feed the material, right? As I said, this is actually typical the schematic of any DED system, where you have the powder is actually coming from the nozzle, right? And then laser is actually coming from the middle, right? So, but most of the time that you will see that the head, which is called a print head, right, will be actually mounted on a z-axis motion, right? So that you can actually avoid too many motions within the system, right? Here, when you actually have this kind of a mechanism, so it will also help us managing with your speed, etc. So most of the time that you will actually see that x and y motion or table will be used as a the base plate, where you actually deposit on the top of x and y, and then you actually move as per the CAD file. So and then I think this is the shielding gas, and then like where it will help in terms of pushing the powder, right? There are different methods that you can actually use it, but typically you will find the shielding gas actually will help pushing your the carrying your powder, right? So you may have even two lines, like where example one line actually carries your the powder, and then other one line will actually protect the area, because when you actually deposit the powder, right? So if you don't even powder or wire, if you don't actually shield it, right, you may find a lot of impurities, and then you will not get the proper in terms of the melt pull, right? To have to get the better in terms of the melt pull, so you need to protect that, or you need to actually shield the deposition area, right? So that's where you actually use primary and then secondary shielding as so, and then you will find other feedback system also, so that you can actually ensure the whatever the deposition that you are actually doing it. So in terms of height, and then in terms of the how the layers are actually coming. Nowadays, a lot of research also actually happening in terms of printing in terms of both precision, or also you'll find not just height but also quality of the component will also improve when you actually go for a feedback system. So these are the some of the components that I was talking about it. So so if you see that very common when it comes to the DED technologies that you will actually find and then I think if you talk about the process point of view, right, as I said, typically you'll be able to achieve anywhere the anywhere the thickness is like 0.25 to 1 mm, but this is actually diameter, but you will also get to 1.1 to 0.5 mm in depth. Basically you can actually penetrate that much amount of the power, the melt pool, so that you can actually penetrate to the previous layer, right? So when you actually inject the powder right into the pool, there, as I said, that is called the melt pool area, right? So as I said, as soon as you actually melt the powder, right, the next step is you need to actually see how it will actually solidify, right? What kind of solidification, or how, what are you doing something forced cooling, or are you allowing to cool under room temperature, and then what your condition in terms of atmosphere, right? So and then there it will actually will decide. So as soon as the powder is actually melted, and then which is basically you create the melt pool, and then it will actually solidifies, and then your actually laser beam will move away from the melt pool area, which is where you actually create the layer, right? So and then this is actually, if you see that typically the track that overlap will be like 25% that you have actually seen, right? So that is a basically, think about, you have the bead, which is almost like 25% of the track width will be the typical overlap in most of the DED process, right? I think first two layers are very important. Again, similar to what FDM technology, you need to have better in terms of bonding between the your subtract and the first few layers, so that you can actually get few following layers better in terms of deposition, right? So otherwise you will end up actually warpage and then so on. Still you may actually see a lot of warpage when it comes to the build plate, right? So and then when it comes to the the technology, so this is how you will actually see that how actually beam will be coming and then interacting your the powder, right? So think about, this is your laser, right? This is actually focusing point. This is actually the reason, right? So you have the spot here, right? This is actually where you're actually the powder is actually coming and then interacting, right? So you may have some time under focused, or sometime you have the over focused also, right? So this is how the the beam look when it comes to see closer look. But you can also see here, if you actually see closer in terms of the how actually the powder is actually coming, right? So you can see this is what actually the powder is actually coming from the side, right? And this is the laser. So this is where the melt the pool. This is where you're actually coming both the powder and then laser is actually coming and interacting at this surface, and then you're melting it, and then your laser is actually will move away from the the melt pool area, which is nothing but you're actually moving your the bed, which is so that you can actually create one layer, or you can repeat the same every the layer by layer, and then you actually get one full layer, right? So this is, if we actually see that you have the different other parameters that like exposed spot region and then critical beam energy density. So this is very important, especially if you want to take advantage of a beam intensity, all that, etc. Of course, there are different height when it comes to the technologies. So typically you'll find anywhere between 8 to 12 the gap between the plate and then the nozzle. But again, it will vary from process to process, technology to technology. But that's how most of the technologies actually works in that. I think, let me see if I can actually play this video. So is it coming there? Huh?
This is coming there.
Coming or not?
Coming.
I should remove out.
No sound.
Can you hear that side sound? Sorry. Yeah. So if you see that, the schematic, as I mentioned, this is actually the powder, right? So you can see that the powder is actually coming, and then this is actually the laser. So you can clearly see that how they are actually interacting at the focused point. And then as soon as the powder is actually being placed there, and then laser immediately will come and then will actually will interact, and then it will melt, and then it will deposit. So now if you look at clearly how the powder is actually coming. So now all will activate, and then continuously it will start depositing. Okay. So can anyone tell me what you guys observed with different from other, which is powder bed fusion technology? Any different observation? Okay. Mm-hmm. Okay, good observation. Any other observations? Right. So as you rightly mentioned, so here you can see that the bed is actually moving, and then component is actually rotating, right? So here we don't need to actually restrict in terms of the size, in terms of the complexity of the component. Like example, of course, when it comes to the complexity of the part, so you cannot actually achieve when it comes to the DED in a 3D or 3 axis, because you need to have actually support structure, right? So in the case of a powder bed fusion, so we had actually support structure, which is basically the powder which was not melted or partially melted, was actually helping us in terms of support structure. But in this case, so if you have any overhanging surfaces or where you need actually support structure, right? So such cases you cannot actually use a simple 3 axis for depositing, otherwise actually material will fall. The reason being, we don't have any support structure, and also we don't have anything that you can actually see. Example, if at all you can see that, like you deposit, of course you can take advantage of a previous layer up to some angle, but beyond which you cannot, it material simply will fall. So what you do here is you actually take advantage of multi-axis, which is 5 axis or 6 axis mechanism, wherein you can actually tilt, right, your the build plate, or you can rotate it accordingly, so that you can actually deposit all the complex or overhanging surfaces, so without compromising on the the size and then etc. Because since you no need to actually worry about the putting the powder on the bed, this much amount of powder, right? So which means you can actually save a lot of material. So you only need to actually deposit this kind of a component. So for that, you need to actually play or plan, path planning and then deposition strategies, right? So that is the most complex when it comes to the technology. But and then advantage is, so you don't need to actually waste any material. Whatever the material that you are actually depositing, it is converting 100% converting it to the actual component, right? So that is advantage. And technically, if we have a gantry of 5 meter by 5 meter, or even 10 meter by 10 meter, you still will be able to actually print such a big large component, because whatever the material is actually required, only you need to actually feed it, right? So that is actually major the difference when it comes to the technology, right? So I think as we discussed different feeding units, like example, we also discussed about the different in terms of source, which is how to feed or how to fuse the material. Another one technology is actually electron beam. So here you can see that the wire is actually coming from the side, right? And then beam is actually coming in the middle, right? So as you see that this is even as I said, if you want to actually increase the speed of the process, right? What are the way? One way is increase the speed, right? Other ways, increase the diameter of your wire, right? Or increase the diameter of, or the size of the powder particles, which is larger, and then bigger the basically the thickness of your layers will be more, such that you can actually increase, and less number of layers are required to deposit for a given component, right? So this is another the DED process, like where we actually have the lasers. I think we have talked about it. So this is the electron beam based, where the electron will be actually used for fusing it. So similarly, we also have other technique, which is basically wire feed, which is wire arc, and then we also have the DED. So these are the different configuration. But again, there are when it comes to the major difference, right? Wire versus the powder, right? So when it comes to the powder, you may have limited material utilization, and then you have the when it comes to the wire, you have 100% feedstock when it comes to capture efficiency, right? Like example here, so some amount of material also will try to fly, right? If you don't actually maintain the proper in terms of the feeding of the gas, right? And you have a when it comes to the printing of some of the composite structures or FGM parts, so you may have better or flexibility when it comes to the powder, because there you can actually mix different composition of a powder. Here you can actually achieve it, but a little bit planning, and then a little more little complex when it comes to the powder, because here you need to have that composition, or you need to have two different wires together will be feeding in same or the same pool, where there you may find different alloy formation, etc. So but if you can actually manage with your compositions and then etc., you will also get here. But it is little more complex than what the powder based, because lot of the powder, it is easy to control, easy to deposit or manage when it comes to the multi-material or composite or FGM structures, right? That's why lot of these components these days, if you see, so they are actually made up of powder based DED, especially for multi-material or DED gradient structures, right? So here you actually push the powder with the help of inert gas. Here you don't need actually any inert gas, you just need rollers to push the wire, right? So here more accurate, the reason being, usually you will find the size of this the powder less than 100 micron, or sometime 82 or between that range. So it is easy to control, or and then here you have difficult to control the wire, right? Sometimes you have the bending issue when you actually push the material. So anywhere it stuck means your melt pool may not go well, right? But disadvantage with respect to the powder based, since the size of the powder is very small, right? Which means you need to actually go for a multiple number of deposition for achieving higher deposition, right? Or increasing the speed of the process. Here we can always example here, usually if you see that the powder particle size, as I mentioned, 80 to 100 micron. Here you will see that the size of the diameter of the wire, it sometimes start with the 0.6, and then you can go up to 1 mm or 1.2 mm. Even you can also go for more the diameter, but you need to have that the laser, so that you can actually melt it. So that is where you can actually find there are cases like where you can also go up to 15 to 20 kgs per hour. You will be able to actually deposit using this technology. So which is quite difficult or impossible when it comes to the powder based technology. Since you are actually using the wire, so it is basically you have that luxury in terms of printing. Of course your layer thickness also will be bigger, or more compared to this thing, because your layer thickness is bigger, means definitely you can actually deposit the bigger component quickly, right? So but if you want to actually go for smaller components, right, you want to actually print some very small component, so there you may have a challenge when it comes to the wire based technologies. That's why you will find a lot of them hybrid additive manufacturing, where you have sometimes like smaller component or smaller features to be deposited, where you can actually use a powder based, and then where you want to have you want to deposit larger component, there you can actually go for a wire based technologies. Now you have to identify exactly which process to go first, which where whether powder or wire based technologies. So as I said, there are different the variants that you will actually find when it comes to the technologies. Laser based, within the laser based we have a lot of lens, and then so many other technologies. Nowadays even a lot of technologies are available, and then this is the technology that I was actually talking about, electron beam freeform fabrication, where NASA actually used in the space for some of the components, printing, or and then I think wire based are very common these days. So if you see that the cost of these technologies, right, when it comes to the wire-based, wire-based comes at a pretty cheap, pretty, example, you can actually have, this setup within, 5 lakhs, or you can actually convert any of your welding machine to, metal additive manufacturing by putting that on your CNC machine or any 3-axis machine, so that you can actually convert into wire arc based deposition. Of course, this is just the old list. I'm pretty sure now almost every institute will have such kind of a facility now, right? So, but initially this technology actually started from these places. If you talk about 20 years back, where you will find not many when it comes to the technologies. So the year the technology actually started, including Nottingham, and then so many other places that you will find now. But this technology is very popular now because of easy to operate, and then easy to, or also can actually afford. Within 10 lakhs, you'll be able to set up this kind of a technology. Um, yeah, so let me play one more video. This will be much interesting. So you can see that this is actually they have kept constant this, and then only the bed is actually chairing, and then you can see that the part, the bed actually changes the orientation as you actually deposit, because the part actually requires that kind of orientation. Otherwise, you cannot actually deposit on 3 axis. So think about, so if you want to actually use a traditional manufacturing process for making this kind of a complex shapes, right? How much planning is actually required, right? Even be it be sheet metal farming, or casting, or any, or even subtractive manufacturing, right? What kind of dedicated tools you need to have when it comes to subtractive manufacturing for making this kind of a component. So it is quite, I mean, difficult when you actually try with the traditional manufacturing. But here you can see how easily one can make such a complex structures without using much tools. So it is almost like 90-degree tilted. Yeah, so you can see that the final component. Okay, so think, as I said, there are few more variants which are developed by, these are the early when it comes to the technologies, they're actually developed between 80s and 90s, some are in 20s. But you'll find a lot of advancements in terms of that recently, lot of technologies. Initially this technology actually started in San Diego National Lab, where and of course now they have the different with the technology, they have feedback system where it can actually correct the height, and then if any defect, automatically you can actually adjust it, right? So these are the layers that you will actually find, like example how the melt pool, and then I think we saw that in the previous slide also. I think one slide that I wanted to show. Yeah, so I think what is the major when it comes to the technology? right? When it comes to the technology, how much you are actually overlapping the tracks, which is basically, think about, this is actually the first layer, and then you have the second layer, and then what is basically the spacing between the these layers, right? So otherwise you cannot actually, other one is you can actually speed up the process by keeping more the space, right, which is less overlap, right? But and then you will not be actually getting the layers are smoothly, or you may have uneven in terms of the between the layer, right? So usually you'll find anywhere 25 to 40 overlap when it comes to the bead width of the each bead, right? So imagine this is the first bead, and then the second bead that you want, if you want to deposit, so you need to make sure at least a 25% overlap. But and then if you actually increase your overlap, and then you actually end up repeating the whole or the process, right? So this is the scan direction. So, and also another most important when it comes to the technology, what is your path plan, right? So imagine you actually start from here, right? And then you actually deposit one layer, and then second layer go like this, right, like this, right? But how about you start here, right, and then you again actually start here, or again you start here, and then again you start here, or like this, or how about like this, right? You can have different path plans, but at the end of the day you are actually filling that area. But what actually will make huge difference, right, when you actually go for a different path planning, right? Your heat generating, you are actually generating a lot of heat while depositing. How you can actually take the advantage of that heat you have actually generated is also important. Say example, so if you actually start here, so you are going like this. Now here you have actually generated some heat here, right? This heat here may be less compared to heat here, it will be more, right? Now, so if you actually take immediately this region, which means you can actually take advantage of already heat is actually available for us, which means less thermal gradient. Any metal 3D printing, if you have less thermal gradient, your deposition will be better, right? So how to take advantage of the heat is equally important. So instead of you start here, you go like this, and then go like this, which means every layer that you are actually going, you are creating, it is like a fresh for you, which means the thermal gradient will be large, right, compared to if you go here, right? But and then if you go here, and then you got one set of this thing, how much you are actually reducing, or how much you are actually taking advantage of that heat is already available. If you are giving a heat, so that is a different story. But if you are already generating, why don't you actually take advantage of that? Now the question is, yes, you have actually heat. What will happen if you actually generate more heat, right? That is also not good. Say example, you start here, you go like this, and then like this, you go like this, and then come like this, and then come inside, you go interior, which is like counter spiral in, right? So when you actually go like this inside, which means you're actually generating a more heat. You're actually generating, it is actually concentrating at the middle of the plate, which at some point it will actually will overheat. And if your thickness of the plate is say less than 5 mm or 10 mm, it will simply will actually will form a hole, because it is excess heat is generated, right? So that also you should not do, right? You need to actually optimize such a that you take advantage of the heat you have actually generated. At the same time, you should also make sure you should not actually overheat the plate. Now, since when you are actually generating lot of heat, your plate, how are you actually maintaining without warpage? right? So without getting your plate, ore or thermal differences. So you need to also actually make uniform heating every time when you actually path plan. So otherwise, since one place you have actually the melt pool, other area maybe you have the fully solid structure, which you actually end up forming a lot of residual stress. Right? How you actually form the residual stresses? So when you actually have repeated thermal cycles or repeated cooling and then heating and cooling, and then if you actually don't maintain uniformity in terms of your temperature, right, you will actually end up generating a lot of residual stresses, right? So that you have to keep in mind. That's why you see that lot of metal based additives, you will actually find lot of warpage. So that is actually come from your actual path plan. So you change your path plan, your stresses actually will change. So that, because since you are actually generating large scale component in this, which is actually repeatedly generating a lot of heat, right? So there you need to actually control your stresses and the temperatures. If you want to control your stresses, you need to actually control the temperature distribution, right? So that is very important when it comes to the especially DED, because in powder bed fusion you are not actually worrying much on the build plate, because you are somehow getting help or support from the powder which is already available. There also first few layers are very important. Here not just the first few layers, but as you actually built also important, because it's keep on distributing your heat. So if you see this, some of the microstructures, like as I said, what I was talking about it. So if you actually go for a more overlap, say example, this is a 60%. This is first bead, right? This is second bead. So you can see that overlap is actually 63%, right? Similarly, if you see that this is a 50, and then this is 50-50, and then you can see that you have the different surface this thing. But if you actually go further, which is 28.4, which is like you are moving away from the beads, right? But and then you further only make a 2.1 overlap, and then you will find a lot of non-uniform surface, right? So and you can also actually see how the beads are actually forming when you actually changes to the overlap, right? So it is very important that if you see this, this is where you're not actually depositing excess material. At the same time, your surface is also not compromising it, because another few layers actually will come on the top. You will be able to actually deposit it, right? Which is, this is the first layer maybe. So and then you can have a next following layers on the top, so that you can actually manage if there is any uneven surfaces. But here, this kind of a scenario, it is not easy, because a lot of uneven when it comes to the the build, right? So these are the some of the example here. You can also find some defect when you actually go for more less overlap, right? But here it is good, but and then you actually decrease the speed of the process. So you need to actually optimize it by playing with your overlap. Otherwise, you end up either creating defects or creating and you can also find a lot of when you actually look into microstructural or the scanning, that where you find a lot of humps and then relative surface and insufficient melting, because you don't have enough overlap. And then you'll also find sometime a different other defect, which is mainly happens because of your overlap, etc. And also you can also see the surface roughness also will vary as you actually changes your edge space, because which is the basically the gap between the two layers, right? So these are the some more the components that many researchers have actually tried. I think this is what I was talking about, like where you can have actually the feedback system, right? So here your sensors actually will help in terms of whether you have actually deposited enough height, right? If not, so sometime what happens, you will have the feedback system which will actually send to the next layer. Say example, instead of depositing 1 mm, so the first layer you might have actually deposited 0.8. The next layer, it will actually compensate by adding extra material. So that's how actually the feedback system works. Of course, there are cases like where you have other defects, etc. How to actually correct it, right? So how to add the excess material is easy, right? And this is actually one of the largest, which is like a aeromat system actually built the large scale, DED system where they can actually print more than 3-meter height components, right? So you can actually see how big. Of course, now the company actually changed it. So you can find almost like 18 kilowatt CO2 laser. So they have used for printing of a large scale the component. So I think we have already seen this we have already one of them. We have the powder DED as well. Of course, we also have the wire DED. So this, I think we have actually talked about it, where this is you have 6 lasers, and then the wire is actually coming in the middle, unlike in the previous slide that where we saw that the power that wire is actually coming from the side, and then laser is actually coming from the middle. But here it is the opposite. The lasers are actually coming from the side, and then wire is actually coming from the middle. And then you can see that how the layers has being formed, and this is one of the components that I've actually deposited. So this is actually the powder based, where the powder is actually coming from the side, and then laser is actually coming from the middle, right? So I think some of the work we have done it. I think you can go through the lab outside. We have actually put. I think our students have actually put some of the slides. So this is the DMG Mori, which is actually very good machine in terms of making a large scale component. Especially they also do a lot of hybrid uh, uh, technologies. So these are the powder feeders. So you can see that how you can also deposit already. So imagine you want to actually deposit the components already available, or you want to actually repair it. Now you can also do the hybrid, which is like machining. Now you can see that after machining, how the components are looking. So yeah, so I think even they have done some of the a comparison where you can actually see these are the some of the mechanical properties that are deposited through different other example lens inconel, and then they also have the different, they are compared with the other the processes where you can see that lot of improvement, or if not in terms of the same properties, but you can actually find the properties are almost closer to the casted components. So I think the commonly materials are used. Of course, nowadays a lot of materials are actually developed. You'll find many alloys are actually tested using this technology, but you will find many variants when it comes to the technologies. I think these are the some of the component. So where you will actually find uh, especially if you want to actually go for some of the gradient structures, right? So where you need to actually change the composition within the component, right? So you have to maintain a different the properties within the component. So where there you actually use this technology for varying the composition, because this can be done by controlling your input, which is the powder. Like there are two ways, right? One is you can actually control the powder that process parameter. So other one is you can actually control or go for a multi material or a multiple material, wherein you can actually change the composition of the input material. Like example, if you talk about material A or material B, so there we can actually change the material composition based on the structure, or based on the or whatever the composition that you want to maintain it. So these are some of the gradient structure that is easy when it comes to this technology, which is not easy when it comes to the powder bed fusion, because varying a powder or the composition there, it will be difficult. But here it is easy when it comes to the, and there are some more components that you will actually find. And again, as I said, so these technologies are also actually good when it comes to repair, right? Not just a deposition, right? So think about, you have the big component, but only a small portion of the part are actually repair, that you just want to actually repair it. Why to remove an entire part? Can you just repair this only this portion? So you can all that you need to actually do that, you actually reference it and then add the material on the or wherever you just need to actually add it. So a lot of places like where you can actually see that easily repaired instead of removing entire component, so that it can actually you can actually fix it, right? So I think since we are running out of time, let me see if I can take you some more video before I can. Let me see what is this video. With Siaki's exclusive. So this is electron beam. In a fraction of the time and cost. Imagine from this to this. In a fraction of the time and cost it used to take. With Siaki's exclusive electron beam additive manufacturing, or EBAM for short, metal 3D printing is not limited by part size, material, or geometry. You can manufacture parts and structures that exceed 19 feet in length, 4 feet wide, 4 feet high, and 8 feet in diameter, made from virtually any metal, including Inconel and stainless steel, and refractory alloys like titanium and tantalum. How does the EBAM process work? Starting with a 3D model from a CAD program. This is the electron beam. Fully articulated moving electron beam gun deposits metal from wire feedstock layer by layer until the part reaches near net shape and is ready for finished machining. Deposition rates can range from 7 to 20 pounds of metal per hour, which is significantly more efficient and cost-effective than selective laser sintering processes that utilize messy powders. In addition, a dual wire feed system can be utilized with the EBAM process to increase deposition efficiency.
as well as to easily switch to different deposition materials. So whether you need to produce a functional prototype or a run of production parts, the possibilities are virtually endless. Our technology partners include the Department of Defense, U.S. Air Force, Boeing, DARPA, Penn State University's Applied Research Laboratory, and Lockheed Martin. Call the metal 3D printing experts at SIACI today and find out how EBAM, electron beam additive manufacturing, can save you significant time and money on the production of your critical metal parts.
Okay, so I think we'll stop here. Any questions? So that is again what kind of a material that you're actually looking. Say example, if you're actually looking for a polymers, yes, why not? It is easy. But all that you need to actually make sure that reference. That by the way, there are actually you know handheld printers, so it is easy. So you can actually, it's like pen type. So it has all the extruder inside the pen, and then so in fact I have one. So it is easy. I think nowadays, especially you know repairing, and then if you want to actually add a free form, or if you want to have your kids to just to play with some simple deposition, so it is very easy. So in fact I have one at home, my home. So my son actually plays that. So he actually does letters and then some different shapes. Yeah, it's easy. Any other questions? So okay, thank you all. So have a nice day. So